What if our universe isn't what we think it is? Recent findings from the James Webb Space Telescope challenge our understanding. A study of galaxy rotations shows an unexpected pattern. Most galaxies spin in the same direction. This contradicts the assumption that the universe is isotropic or uniform in all directions. Instead, it suggests a cosmic alignment, and even raises the possibility that our universe could exist inside a black hole. In this video, we'll explore JWST's surprising discovery and its implications for cosmology. The JWST is transforming our view of the early universe. Designed to peer back more than 13 billion years, IT can study galaxies as they existed shortly after the Big Bang, offering a direct look into the universe's infancy. In this study, led by Lior Shamir at Kansas State University, researchers examined 263 galaxies captured by JWST. These galaxies formed roughly 300 million years after the Big Bang, making them some of the earliest cosmic structures ever observed. The key finding? About 60% of these galaxies rotate clockwise, while only 40% rotate counterclockwise. This imbalance may not sound dramatic, but statistically, it's a meaningful deviation from what we'd expect in an isotropic universe, where rotations should balance out over large scales. This isn't the first time such hints have appeared. Past surveys using the Hubble Space Telescope suggested similar directional biases, but those samples were smaller and less conclusive. JWST's advanced imaging has made these patterns harder to dismiss as coincidence or observational noise. Why does this matter? In the standard cosmological model, the early universe should not favor one direction of spin over another. Over time, galaxy rotations are expected to even out randomly. But these results imply the early universe may have been born with a directional imprint, a sort of cosmic handedness that influenced galaxy formation. This raises big questions. Was there a cosmological axis, a large-scale directional structure built into the universe? If so, what caused it? And could it reveal something deeper about the conditions that gave birth to our universe? This discovery challenges the idea that the universe is random and uniform at its largest scales. If confirmed, it suggests an underlying structure shaping the universe's early days. One of the most intriguing explanations for these findings is rooted in a decades-old idea known as black hole cosmology. This model proposes that our universe may exist inside the event horizon of a massive black hole in a larger parent universe. In this framework, the Big Bang wasn't a singular creation event. Instead, it could have been a gravitational collapse followed by a bounce, a process where matter collapses into a rebound under extreme quantum and relativistic effects, forming a new, expanding space-time region. How does this connect to the galaxy rotation pattern? If our universe originated inside a rotating black hole, the spin of that could be imprinted on the fabric of the universe. This inherited rotation might explain why early galaxies show a clear preference for one spin direction, a cosmic fingerprint of the black hole that birthed our universe. This concept isn't speculative hand-waving. Physicists like Nico Poplawski have explored how Einstein-Cartan gravity, a variant of general relativity that incorporates particle spin, could prevent these from collapsing into singularities. Instead, collapsing matter reaches an ultra-dense state, then rebounds, forming what we observe as an expanding universe. The Hubble tension. The persistent discrepancy in measurements of the universe's expansion rate may be more easily resolved if our universe's expansion history differs from standard Big Bang predictions. JWST's impossible galaxies, observations of surprisingly mature, massive galaxies at very early epochs, might make sense if some structure or matter was inherited from a pre-bounce phase, accelerating galaxy formation. While still speculative, this theory offers a unifying explanation for several anomalies, linking the spin bias in galaxy rotations, the presence of unexpectedly old galaxies, and large-scale cosmic alignments into a coherent framework. If our universe is indeed the interior of a black hole, it changes how we think about everything, from the Big Bang to the fate of the cosmos. It would mean that the Big Bang wasn't the absolute beginning, but rather a transition, a bounce from one universe's collapse to the birth of ours. It would also reframe black holes, not as singularities where physics fails, but as gateways to new universes, each with its unique properties. But before embracing such a paradigm shift, these findings require much stronger evidence. The current analysis is based on 263 galaxies, a solid start, but far from definitive. Researchers need to examine thousands of galaxies across different regions of the sky to confirm whether the rotation bias is universal. We also have to consider observational biases. Could our position in the Milky Way or the way JWST images distant galaxies affect how we interpret their spins? These are questions that require careful testing before any conclusions can be drawn. So, what's next? Expanded surveys. JWST will continue its deep field observations, capturing thousands more early galaxies for study. Search for relics. Scientists will look for primordial black holes or other remnants that could support a bounce universe model. Revised measurements. Cosmologists may need to reevaluate distance and expansion calculations, which could also help resolve existing tensions in cosmology. Whether or not the universe hypothesis holds up, some data is already reshaping our understanding of the cosmos. It's forcing us to revisit foundational assumptions and explore bold new possibilities for how the universe began and what it truly is. Could our universe be inside a black hole? While the evidence isn't conclusive, JWST's findings suggest it's a question worth exploring. The discovery of galaxies with a shared spin direction hints at a possible alignment inherited from a black hole. As we gather more data, we'll uncover whether this pattern holds. Stay tuned as we challenge our deepest assumptions about the universe's origins and structure.